Okay, so I have two more examples that I want to show you. And, maybe apologies if I am dragging you on those kind of side path, but again, I wanted to show you possibility with those tools, somehow related also to combustion, of course. So I have two more examples and to finish these lectures. So I want to talk about something that is related, even if you don't think it is, but it's related. And I get involved in those projects sometimes, I love them. So okay. So the reason why I have this image here is that, that was the hand of Sky, you can imagine. And these things, pretty soon, there's a lot of applications, okay, that maybe we're not there right now, but we will soon. What we are there for sure is this guy here, that is a heart. So this is a heart that can be implanted, medically implanted for problems. And the reason why I want to mention this, and I'm sure many of you, I don't know, maybe in this room, or know of someone that have some kind of a device in the body, or had the surgery, or I have the hip replacement, or, so the idea is that when you have something like this, okay, or a foreign body in your, something in your body, that could be a great place for infection, okay? And so what happens is that you can have something like this that get infected, and people usually don't worry much because they say we have antibiotics, right? Well, the problem is that if you have something like this, that is a catheter, okay? And if you have an infection here on this catheter that is going inside the body, it's easy. You're going to remove the catheter. That's what people do. Or you take some antibiotic quickly. But then if, for example, the heart valve that I showed you before become infected, that means open heart surgery. So there is, you need to remove it. If your hip gets infected and antibiotics are not functioning, you need to remove them. So the infections is becoming a very, very important point here. And in some cases, when the antibiotic do not respond, you have to take them out. So it's a big deal. So I want to talk for 2 seconds about something that, how many of you know resistance? How does it happen? Yeah, anybody. Could you know medicine? How does it happen? Yeah, go ahead.
Well, the non-resistant ones are weeded out, so only the resistant bacteria survive and proliferate.
Yes.
And then you have...
Yeah. So this is a concept that sometimes is not very, known, because people talk about cancer, talk about a lot of other things, but no one says, hey, antimicrobial resistance. And so what it is basically, as I was mentioning, is the idea that eventually there are already cases in which antibiotics do not work. So you have an infection, you take your antibiotic, and nothing happens. So what happens, the reason for that is that they develop resistance. So those bacteria are now somehow not responding to the medicine that they receive. And this is eventually based on evolution, okay? Bacteria are going to be much smarter than us. No matter what, they will always develop resistance. But if you think about this, the plot here shows that people are not developing antibiotics anymore. And the reason why pharmaceutical companies, they don't have a lot of this is because they don't make money. If you develop a drug like Lipitor that people take for cholesterol, right? They will take for the whole life. Antibiotic usually you take for a week, 10 days. So if you think about revenues, antibiotic is not being on the top of the list for many pharmaceutical companies. And so what this plot is showing you is that people are not developing new antibiotics, but at the same time, resistance, the bacteria, is going up. So eventually, if we don't do anything, this is a catastrophe, because it's like going back to an age in which basically even a small cat could kill you, because there was no antibiotic. And this is a huge problem. So in US, there are 2 million of people that develop antimicrobial resistance each year. And there are 700,000 deaths per year worldwide. Antibiotic does not help anymore, okay? So the reason why I'm bringing, I promise I'll bring you back to a carbonaceous nanoparticle, is that this is something that was very interesting to me. The idea was maybe thinking about some molecules that could be useful for those scenarios. So I want to show you what we've been thinking about. So this is a lab biofilm. So have you heard of MRSA, so methicillin-resistant Staphylococcus aureus? It's basically a bacterium that is resistant to methicillin, the molecules, right? And so what happened is that you keep giving this medicine, the drug, and it's not going to die, basically. It's always lethal. Those are one of the main responsible for infection in hospitals, for example. You get a lot of those infections. We heard a lot during COVID. The people went there for COVID and then got infections, right? So again, I need my molecular dynamics. I need some information to study this problem. And so working with medical people, but also with people from computer science, we've been looking, and especially material science, we were looking at this. And so the question is, can we think of some structures that somehow interact or can interfere here? So the goal, and this is a work in progress, absolutely not finished, is can we develop some kind of nanobiotics? So an antibiotics, but at the nanoscale. Now, why I was very much interested in this is a good question, because why nano? Now I know a lot about nano from combustion. Why about nano? Because when you take a small antibiotics, okay, like something the size of a benzene, for example, whatever, it's much easier for the bacterials to develop resistance because they have only one way to attack the bacteria. But nanoparticle, you can design the way they want. They can have different shape. You can hook them with many ways to attack the bacteria. And so the likelihood that they develop resistance, it's much lower. That's the reason why we got interested in this field, the nanoscale. Also, if you think about this, do you know the lifespan of a bacteria? It's like 20 minutes. So in an hour, we have 3 generations of bacteria. And each generation has a chance to develop resistance, okay? So they are going to be always outsmart us. The only thing we can do is to slow down. That's all we can do. So for me, do molecular dynamics, I need first to understand what I was dealing with because I had no idea. And so this is a schematic of a biofilm. A biofilm is some kind of gooey stuff, here the yellow ones, is a fortress that the bacteria produce to protect them. So you have, even on this surface, the same things. You have some bacteria, and the way they protect them is with this kind of a slime, yellow. So they build a fortress from themselves. So here what you see, green, purple, are different bacteria, so different. And so I needed to go down in size more and more. And so what you see here is a blow-up of this yellow section in which the green and the blue couple the 2 bacteria. But here, my yellow stuff is formed with a lot of, there is DNA, there are proteins, there are a lot of those structures, okay? So the question was, I would really like to break down this yellow stuff so that the bacteria inside are no longer protected. So one of the reasons why, for example, they don't respond to antibiotic is that antibiotic cannot reach them, especially in these biofilms. They cannot get through. So I have to start from building block. And so I start asking for this Staphylococcus aureus, because they're different bacteria, so different. What are the main protein that I have here? Okay. And so for them, one protein is, actually this is an amino acid, but is just to give you an idea, this is carbon, hydrogen, there is oxygen also. Anyway, it's called PSM, it's relevant in this moment. And so what you do is that if you put a lot of amino acids together, you get a protein, okay? And that's what I was interested in. So I started from this as a building block. And then the idea was, how do they form a bigger protein? So think about a pH, same things. How do they get together? We did with dimerization. How did they get together? How did they grow to bigger structures? So we started doing some simulations. I don't know if this is working well, but this, yeah. Oh, sorry. Here. This works. No, it's not working. That's fine. So we put together, those are 20 of those small amino acids that I just showed you. And the difference between this left and this right, if the movie were to work, is that those are different alpha 1 and alpha 3. There is a little bit of different configuration in those amino acids. And so the reason why I studied both, those are the two main representative of those structures of the lime. And if you look at their aggregation, they form different structures, okay? So this is basically ordered, if you want, but this is more messy. Do you see there is a lot of things going on? And I need this information. I need to know if I'm coming in with a molecule, what am I facing? Am I facing something that has an order or something like this? So we built a little bit bigger structures. This was still too small. And those are some results. So this is a protein, actually. And again, this detail is too much for protein biology, but it's not the point. The point is that this is the structures that you form in the yellow stuff. And so again, this is very ordered. And this one instead does these weird structures here. So whether you are meeting an PSM alpha 1 or alpha 3, you get these different interactions. And the point is that also in between those two columns, if you want, there is a lot of hydrogen and other interaction that is there. So what we did was taking some of those, I was very much interested in carbon quantum dots that I showed you also before. And what we did was, how about we add the carbon quantum dots to those kind of system? What happened to, I need to understand what's happening. And again, I am very far from reality, but at least the idea was to give some insight about that. And so we look at some simulations with these structures and then quantum dots inside. And I want to show you just the local interaction that we got. So if you look at the top here, what you see is that the beginning of the structure I showed you. So if you take two of those building blocks, the PSM, and you let them in molecular dynamics by themselves, they agglomerate. They show the structure that I showed you. And so you will go into the formation of those fibers. If instead you add a nanoparticle to this, and this is a quantum carbonaceous carbon quantum dots again, what you see, and those are three different snapshots of molecular dynamics, is that those two guys, instead of interacting with each other, they will start interacting with the nanoparticles. They are attracted, and you can see also that there's kind of unraveling the protein around these nanoparticles. So what does that mean? Look here, instead of growing again in this way, they start in a weird conformation because they are distracted by these nanomaterials, if you want. And so from molecular dynamic simulations, this is the result you get, because not only snapshot, remember, you need to somehow also quantify. And so if you look here, what this is showing is that if you are in the red one, if in your box there are only those building blocks, you will see that the distance between the two of them is going to be 0.9 nanometers, okay, whatever. So what they do, they form a dimer. They are here. In the moment you're adding a nanoparticle, now you have three things in the system. Now I have, so my green stuff here. What you see is that this peak is going to broadening here, and you have different configurations that are formed. So no longer, there is something also at this peak because of the distance, but there is a lot here, there is a lot in this other peak and in this other peak. So those are different configurations which a nanoparticle somehow distract the building blocks. And so, in other words, what's happening is that in the moment you are adding these carbon nanomaterials to these structures, you are disrupting or influencing the building of these proteins. And so those proteins are basically the main thing, that is here, right, that I show you in the slime. So if I manage, basically, the idea was if the carbon quantum dots comes in and doesn't allow those proteins, so it breaks down those proteins that they are here, then basically they are the building block of the yellow stuff. You don't form the yellow stuff anymore or create damage, okay? And so the bacteria can be exposed. So we tested this experimentally always, remember you have to do that. And this is the biofilm that I showed you before. So this is all bacteria by themselves. And then here is the same bacteria adding 50 microgram per milliliter of this graphene quantum dots. And here he was adding more and more. And so what you see is that the addition of these nanomaterials cause actually the formation of those pores. It breaks down the biofilms somehow, okay? So that was a great result, but you were still doing work. We have to keep pushing this because this was one case. But the idea is that with these same tools, what you can do is basically now thinking about designing of some nanostructures that, that you can have or you are thinking about and test whether they can also have an effect on that. So a little bit of a stretch, okay? But I wanted to show another application that molecular dynamics. So any questions about that? Outside your, I confuse you too much this. So last step, and then we're done. Now, great, we have all those things, but we wanted to get more general. So what we have been doing lately, and this is really the last things that we published actually in 2023 and a few more in 2024, but this is the last things we have done. So I've been looking at interaction of carbon-carbon for something like this, for combustion, in which you have maybe a lot of those bigger structures, they get together in the box. I've been looking at some carbon nanoparticle with the protein. And then there is a lot of literature on protein-protein that you can find. And so the question was, can we find a way, a general way, to describe the interaction at the nanoscale? I didn't care if it was protein or a nanoparticle, but I wanted something very general. So what is the big challenge is that? The big challenge is that the interactions are often very specific to one type of nanoparticles. Okay, that was problem number one. And there is a lot of data is usually required. I told you when I do a machine learning, and there is a lot of data on proteins. Proteins are much easier than nanoparticles. A protein is just a sequence of amino acids. I just showed you. You have a building block, and then you repeat. That's it. I mean, relatively easy, but there is a lot of data on protein-protein interactions. Nanoparticle, they come in all shape, forms, chemical composition. You can have a sphere, you can have a pyramid. You can have a metal, you can have a carbonaceous nanoparticles. You can have charges. You know, a charge distribution on something that is spherical or that is a pyramid, and so concentrated in one of the vertices, it's completely different in the types of interaction. So way more complicated. And the other thing is that there is no much data. So one of the first tasks that we started, and we're still doing, is to curate a database of carbon nanoparticles with the proteins. You know, and so that means extracting from the literature and insert all the details that we needed for this data set. And so there is a lot of protein. This is what we have been looking at, and this is what we have been looking at. So can we develop a general method? And so as a last point in this discussion today, and then I'll stop because I think I am diverged too much, I want to talk about Necklace. That is the code, the last code that we developed, is a way to generalize the representation. It doesn't matter if it's a protein or a nanoparticle. And so what Necklace does is basically decompose any nanostructures into some coordinates that you then plug into a neural network, machine learning, to get the propensity of those two structures to interact. So the beauty of this idea was that it was trained only on protein-protein interaction as a training, and then as a testing, it was tested on nanoparticles. So how does this work? Well, somehow it brings together what I taught you yesterday and the last 2 days. So there is some atomic in structures. this is a nanoparticle, for example, and this is a protein, complicated. Those are the atomic structures. You need to have some information about that, of course. And then what you do, you remember coarse graining that we talked a little bit? And so you transform these complex structures, you simplify, and you have now some coarse graining sites that describe the nanoparticle. One of the issues is how you describe the features of the nanoparticle. So this is part of the challenge. But then you also take into account the local features in the environment. So is this in water, for example? Is this in the gas phase? What is the neighbors that you have? And so once you plug all those information and somehow you translate them in characteristic of features that go into your input, the machine learning, what you get out of this is basically, I don't know, a prediction of the propensity of those two to stick together. So the way we did, let's see this work, the coarse graining. Does it work here? Oh. So it decomposes any structures, it decomposes any nanostructure into clusters of beads. So you can see here. And what it does, wow, is I had to do something also the last day, guys. So let's go, I don't know.
Here we go again.
Yeah. Well, I was almost not too far from being done. I don't know what's happening.
TV screen. That's your connection.
Oh, it came back and then disappeared again. I didn't have a lot of slides left. There's been an adventure. It's okay. I had just a few, I think 3, 4 slides, I don't remember anything. But the idea was that with this necklace, that I think something that we are really looking forward to, develop more. We were able to translate our...
Keep talking right in that spot. I'm going to go right there.
No, don't. It's okay.
I got to make a call.
The idea was that we are now able to predict the interaction between a nanoparticle and nanoparticle, but also nanoparticle and protein. So we trained only on protein-protein interaction, but we're able to reconcile and been able to engulf also the carbonaceous nanoparticle. And so I have some visuals that I want to show you. It's okay. And it was between carbon and protein. And this is for a molecule that has to interact with a specific protein, carbonaceous nanoparticles. And another one was also carbon and carbon nanoparticles. So there are a few more details if you ever are interested in this topic. But I think this is really unique. This is really new. And it goes also with the combustion. So not only able to predict what I extended this machine learning that I showed you before with Lasso. And so now we go also in nanoparticles in the combustion. And not only that, but also with the protein. So I didn't have much more to add except some examples to show. But yeah, that's okay. Oh, I'm sure.
Oh, your laptop just wants to sleep.
Oh, we have plug and replug. Okay, thank you so much.
No worries.
I plugged it and unplugged it. Okay, so I wanted to show you that. And so the way it's doing that, you see that this is a kind of, the coarse graining is not just, again, you take a coarse graining and you decide this is a point. But the way you locate the beads of this coarse graining is done in a way that you are able to capture the molecular shape and the symmetry of the molecules. Okay, so you retain some of this information. And then what you do is basically in this case, was more complex. So this is a carbonaceous nanoparticle with 6 member rings. But what if you have something that is a little bit convoluted with the sulfonate group and the hydroxyl group? So you need to pay a little bit more attention there. And then in that case, we were looking at something that is more like this, in which there is a core. Sometimes. So the coarse graining needs to be done carefully for the system. And okay, this is the gram. And then, so let me show you just an examples. And that goes on this protein. Now, this protein is a huge, and it was very important because these are all the things that it can do in the body. So from metabolism, apoptosis, the death of the cells, of course, and then that's very important. And so what we were interested is looking at the designing of some molecules, micromolecules, that can attach on the protein. And so this is called molecular tweezers. And what you see here, actually, this is the prediction, but this is also what experimentally was measured. And so this kind of the code is able to reproduce exactly the interaction site of the tweezer, so this kind of nanostructures on this protein. And so this is the true binding configuration that you see for this system. And so basically what this is telling you is that the code is able to reproduce the binding site and therefore also the properties that are important for those interactions. It just should show you that PSM alpha 1 is very GQD, have a potential as antimicrobial in this previous slide. And so what we wanted to do was predict the known interaction between PSM alpha and GQD. And so we did the same things. We did the protein like this, became coarse graining like PSM alpha because we know the ground truth. We know a full molecular dynamics, what it is. And so we did the same application for those systems. And then what you can see here is somehow the predictions. And this is a very good alignment in terms of results. So I don't think I did much more. Oh, the last example I had. Now, with the same necklace, can I predict carbon-carbon nanoparticle? Because, you know, I don't want to lose that. That is the most important part also. So we look at atomistic simulation. We put a lot of big pHs in the box. And you can see that, of course, all atom simulation will give a different configuration when they cluster. If you have those flat, then some can go like a sandwich type. Some can go perpendicular. So you have those structures. What we did was to coarse graining them, again, this sequence. And then the molecular dynamics, this is the force field that was used for all the configurations. And so the prediction that we have that were done also with the necklace, what it does can be used to parameterize the molecular dynamics, the force field. Okay, and what we saw here that basically you have a great agreement between the interaction between all those carbon atoms in the structures. So bottom line, even if we are pure without protein, although we train on protein, we can reproduce the behavior of those structures. Okay, and their tendency to get together and to form those weird blob. So you can do way much more. Those are just examples. And another thing that I want to here to emphasize is that you can change carbon to silicon and nothing changes in the code. I mean, the idea, the algorithm is exactly the same. And so as we did with the pHs and nanoparticles, carbonaceous you can do with silicon, and same things with this approach to get the sticking probability. So developing a model also for other, this case was a silicon, but it could be any other material. So the idea is that you get some feeling about what are the scales that you are interested in, what are the properties that you are interested in, and then you pick the right tool for that with the consideration that I showed you over the last couple of days. But then there is a world of application that you can do. So the idea, I guess the final message is get excited about this field. Don't just talk about Soot, but talks about more than that. talks about carbonaceous nanoparticle, carbonaceous material, because then you go from an application you design all the way to biology if you want to dive into that. And my last slide, this is all the kids, kids, I have to say, compared with me, but the material that you have seen comes from them. So without them, it will not ever be possible to do anything here. And so I want to acknowledge that. And I think this is my last slide. So thank you for bearing with me for those 3 days. I guess the journey was a little bit different, but I hope that you got something. And if you have any questions or anything that I can help, I got some questions yesterday also via email, and I was very excited. I like questions. So if even in the future you are thinking about a system and you say, okay, I'm thinking to use this tool, what do you think it could be right or wrong? What are the limitations? Which one should I use? Feel free always to email me. I just enjoy that, okay? So thank you so much for staying with me, and have fun with remaining on the class. Thank you. Any questions? Anything that I can answer? If not, well, I'll see you later. Also, there is the career panel, so we can talk about other stuff. But in the meantime, thank you so much for coming, and thank you for staying with me for those 3 days.